Hello Calc 3, welcome back to another video. In this video we'll be covering section 15.2 on double integrals over general regions. So remember that in the last section, section 15.1, we built up the notion of a double integral for functions f of x, y in two variables, but we only built up the integral for rectangular regions in the plane inside of the domain of our function f. And in this video, section 15.2, we're going to generalize that double integral so that we can take the double integral over non-rectangular regions as well in the plane. So this section is all about just building up that, that double integral for general regions here. So again, let f of x, y be some continuous function over a general region R in the plane. So R is just some region inside of the plane that happens to be a part of the domain of our function f. And again, we will subdivide R into small rectangles with lines that are parallel to the x and y coordinate axes. So if you look over at the diagram, you can see that. The region that we're worried about is the region outlined in blue. And notice that some of the rectangles are not fully contained in R. And so all of the portions of the rectangles in blue in the diagram to the left would be the rectangles that are not fully contained in R. The partition of our region R is only going to consist of all of the small rectangles that are completely contained in R. So all of those rectangles that have, where a portion of them is blue, those rectangles will not be considered part of the partition of the region R. And here's the key difference here for general regions is that some of those rectangles are not going to be inside of our region fully because our region is not a rectangle in this case. But as the norm of our partition goes to 0, it is true that more and more of the region is going to be covered by the partition. So you can think about that as, if you look up at the diagram here, if I keep making the partition smaller and smaller, then I can get more and more rectangles inside of the region completely, and eventually it's going to be so close to covering the entire region that it won't matter anymore. So the limit as that partition, or as the norm of the partition goes to 0, is still going to be a Riemann sum similar to that of which we had for general rectangular regions. So again, once we have a partition P with n rectangles, we can number those small rectangles as r sub 1 through r sub n. That would be fine. And the area of each of those rectangles is denoted delta a sub k, which is just equal to the width of the rectangle times the height of the rectangle. And we still choose a point, x sub k, y sub k, inside of each of the rectangles to construct a Riemann sum for that particular partition. So again, if you look back up at the diagram, we've picked that point in red inside of that small rectangle, and we've called it x sub k, y sub k. Then the Riemann sum for our partition and the points that we've chosen is denoted s sub n, just like we did in section 15.1, and it's equal to the sum from k equals 1 to n of f of x sub k, n sub k, or that should not be an n, x sub k, y sub k, multiplied by the area of the kth rectangle. And the double integral is again going to be the limit of those Riemann sums as n goes to infinity, or as the norm of our partition goes to 0. Either one will be fine. So the double integral of f of x, y over the region R is equal to the limit as the norm of the partition goes to 0 of the sum from k equals 1 to n of f of x sub k. I don't know why I keep putting n sub k, but that again should be a y sub k. X sub k, y sub k times the area of the kth rectangle. And it is not true that the norm of the partition, as the norm of the partition goes to 0, it doesn't always imply that the partitions will cover more and more of R. So I tried to give an intuition as to why it's the case that as the norm of the partition goes to 0, you cover more and more of the region. And for general regions, that is true. So as the norm goes to 0, we do end up covering essentially the entire region. And so the limit of the Riemann sums does give us does give us the appropriate volume underneath the surface over that region, but there are certain regions for which you can have the norm of the partition go to 0, and yet it won't cover that whole region. But for this class, we're not going to run into any of those kind of regions, so all of the regions that we will consider in this class, the norm of the partition going to 0 is sufficient to imply that the entire region is going to be covered in the limit. So the double integral for general regions will have the same geometric interpretation as it did in section 15.1, where it represents the signed volume between the xy plane and a surface in space represented by the function f of xy. So we will talk about that here a little bit and also develop a method for calculating double integrals over general regions. So let f of xy be a continuous function as per usual, and assume that it's positive over a general region R. We define the volume between the surface z equals f of xy and that general region R to be the double integral of f of xy over the region R. So I have a little bit of a diagram here on the left, which again I took from the book. So our general region R is the region down in the plane, and then we have our surface z equals f of xy above the plane, and the double integral is going to give us the volume between those two regions. So notice that in the plane, the region R is going to be bounded above by a function this time. So in section 15.1, because we were worried about rectangular regions alone, the rectangular region would be given as R where, I shouldn't put 0, R where x would be between a and b, where a and b are some constants, and then y is going to be between c and d, where again c and d are some constants. In this case, our region R is defined so that y has to be between two functions. So instead of constants, now we have, okay, x is still going to be bounded by a couple of constants, but y is going to be bounded by a couple of functions. So functions in x. So x is going to be greater than or equal to g1 of x, or excuse me, y is going to be greater than or equal to g sub 1 of x, but it's less than or equal to g sub 2 of x. And you can see both of those functions are written here inside of the plane. So that's the key difference here, is that our region is not purely rectangular, where y is just going to be bounded by a couple of different constants. Y can be bounded by functions in this case. And we'll see a little bit later that we can also define double integrals where the region can be described as x being bounded between two functions of y, and y being between two constants. But we'll get to that in a little bit. So our region R is going to be bounded below and above by these two functions g sub 2 of x and g sub 1 of x, and it's bounded on the sides by constants, x equals a and x equals b. Then the area of that cross section inside of our solid here, so a of x, which is right in here, the area of that cross section is going to equal the integral from g1 of x to g2 of x of our function f of xy dy. So notice the difference here is that in section 15.1, the limits of integration were always constants. But now we introduce integrals where the limits of integration can be functions in and of themselves. And in this case, those limits will be functions of the variable x. And the volume of the whole solid will equal the integral from a to b. So now we're looking at the limits of integration for x. So we have the integral from a to b of this function giving the area of the different cross sections a of x dx. And so we can take both of these pieces of information and say that the volume of the whole solid is equal to the integral from a to b of the integral from g1 of x to g2 of x of f of xy dy dx. So here we've expressed the volume, or the double integral, as an iterated integral where the inner integral is going to have limits of integration that are functions of the variable x, and we'll give some examples down below so that we can see exactly what that looks like. So if instead of the r that we have above, let's say that the region in the plane is like the following region that I have in this diagram, we can use cross sections in the other direction. So now we're going to have cross sections that are perpendicular to the y-axis, whereas the cross sections from this diagram would be perpendicular to the x-axis. And again, in this case, we're going to integrate with respect to x first, and then integrate with respect to y. So the area of the cross section, which is this blue plane here, the area of that cross section is going to be equal to the integral from h sub 1 of y to h sub 2 of y of f of xy dx, where again, x is going to be bounded above by this function h2 of y, and x is going to be bounded below by this function h1 of y. So you can think about that as you can draw lines from x equals 0 through this region in the plane here, and you can ask yourself what describes the place where x is, or where that line is entering the region in the plane, and what describes the place where that line is exiting the region in the plane. So that line is going to be entering the region in the plane along that curve x equals h sub 1 of y, and it's going to be exiting at the curve h sub 2 of y, which is why h sub 1 of y is going to be the lower limit of integration, and h sub 2 of y will be the upper limit of integration. So again, that'll give us the area of these cross sections that are perpendicular to the y-axis, and now the volume is going to equal the integral from c to d, because y is going from the constant c to the constant d for our region here. So that's going to be the integral from c to d of a of y dy. And then we can take both of these pieces of information, put them together, and we get this iterated integral here. So we have the integral from c to d of the integral from h sub 1 of y to h sub 2 of y of f of xy dx dy in this case. And notice that the order of integration is switched here, because in the second example, we are using cross sections perpendicular to the y-axis. In the first example, we are using cross sections perpendicular to the x-axis, and that will change the order of integration. Okay, and this leads us to the big theorem for section 15.2. If you recall from section 15.1, we had a theorem called Fubini's theorem that said that we could interchange the order of integration over rectangular regions as long as our function was continuous. And now we're going to have a stronger form of Fubini's theorem for general regions in the plane. So if we let f of xy be some continuous function on a general region R in the plane, then we have these two facts here. So one, if R is defined by the fact that x is going to be bound between two constants, a and b, and y is going to be bound between two functions of x, which we call g sub 1 of x and g sub 2 of x, where g sub 1 and g sub 2 are both continuous functions where x is on the closed interval between a and b, then the double integral of f of xy over the region R is equal to the following iterated or repeated integral. So we have the integral from a to b of the integral from g sub 1 of x to g sub 2 of x of f of xy dy dx. So notice here that the order of integration is dy dx because y is bound between two functions of x, and x is bound between two constants. And secondly, if R is defined in the following way, where y instead of x is bound between two constants c and d, and x is bound between two functions of y, this should be an h sub 1 of y, so x is between h sub 1 of y and h sub 2 of y, where again the functions h sub 1 and h sub 2 are continuous on the closed interval from c to d, then the double integral of f of xy over the region R is equal to the iterated integral where we have the integral from c to d of the integral from h sub 1 of y to h sub 2 of y of f of xy dx dy. And now we have that the order of integration is with respect to x first and with respect to y second. And so what this tells us, or at least one of the things that this tells us, is that if we have some general region and we can write it in either the way corresponding to the first part of Fubini's theorem or corresponding to the second part of Fubini's theorem, then we can again change the order of integration as long as we make the appropriate substitution between these functions of x and these functions of y. But there will be many times where you have a general region in the plane and you can describe it in either of these ways. And so you can perform the integration in two ways. You can switch the order of integration. And we'll talk about that a little bit as we get further down. Okay, so the rest of the video is going to be devoted to going through a bunch of different examples where we're calculating double integrals over general regions, with a little bit of a break where I'm going to talk about some of the properties of double integrals, but for the most part it'll just be examples. So let's get to the first one here. Let's say that we want to find the volume of the prism whose base is the triangle in the xy plane bounded by the x-axis, the line y equals x, and the line x equals 1, and whose top lies in the plane z equals f of xy, which is equal to 3 minus x minus y. So when you end up with a problem like this, the first thing you want to do is sketch what the region looks like in the plane. So in our case, the region in the plane, which we will call capital R, looks like the region that I have drawn in the diagram to the left. So you can see we have our line y equals x, we have the line x equals 1 in red, and then we have the x-axis in blue. And the region that is bounded by those three lines is that triangular region that I filled in green. So we know that the volume of this prism is going to equal the double integral of our function f of xy over the region R. And notice that our region R in the plane can be described as the region where x is bounded between 0 and 1. So we have x equals 0 over here, and then x equals 1 over where the red line intersects the x-axis, and where y is bounded between 0 and x. So again, y is going to be bounded above by this line y equals x, and it's going to be bounded below by the x-axis. So y has to be between 0 and x. And this is what I mean by y being bounded by functions of x. So you can think of g sub 1 of x is equal to 0 in this case, which is less than or equal to y, which is less than or equal to g sub 2 of x, which equals x in this case. So the double integral of f of xy over the region R by Fubini's theorem is going to equal the iterated integral, where we're taking the integral from 0 to 1 of the integral from 0 to x of f of xy dy dx. And notice that we're integrating with respect to y first because we're taking cross sections that are perpendicular to the x-axis. Another way to remember this is that if you have your limits of integration for that inner integral here, if your limits of integration are given in terms of x, then you're going to be integrating in terms of y first. If those limits of integration are given in terms of y, then you'll be integrating with respect to x. So that's another way that you can remember it. But anyways, so now in the second step, we're just going to substitute in for f of xy, which is equal to 3 minus x minus y. And now we're going to take the integral of 3 minus x minus y, where we treat x as a constant, and we integrate with respect to y. So we end up with 3y minus x times y minus 1/2 times y squared from 0 to x. And now we can plug in x, and we get 3x minus x squared minus 1/2 x squared. And if we subtract what we get when we plug in 0, we would just get 0. So we're not going to worry about that. And so we end up with the integral from 0 to 1 of 3x minus x squared minus 1/2 x squared dx. and now it just becomes a problem from Calc 1. So I simplified a little bit, combined the x squared terms to get a minus 3/2 x squared, and then you can take the integral, which ends up being 3/2 x squared minus 1/2 x cubed, again from 0 to 1. So we take 1 and we plug it in, and if we take 0 and plug it in, then we're just going to get 0. So ultimately this equals 3/2 minus 1/2, which is just equal to 1. So the volume of this prism that is bounded above by the plane z equals 3 minus x minus y over the region R, this triangular region in the plane, is going to equal 1. Okay, so now let's move on to the next example. The goal of the next example is to show that sometimes, even if you can integrate with respect to x first or with respect to y first, you should be wise about which one you choose. Sometimes the integration will be significantly easier if you choose to integrate with respect to x first or with respect to y first. So in this case, we want to calculate the double integral over the region R of the function sine of x over x, where R is the triangle in the xy plane, bounded by the x-axis, the line y equals x, and the line x equals 1. So our region here is going to be the same region we had from the first example. It's just that triangle that I have drawn in the diagram there. So in this case, I want to make it known that we can define the region in a couple of different ways. So before, we said that the region could be described as the region where x is between 0 and 1, and y is bounded between 0 and x. But we could also say that y is between 0 and 1. So you can look at it as y is between 0 and 1 here as the height of the triangle, and x is going to be bounded below by y. So x will be bounded below by this line y equals x, and it's going to be bounded above by the line x equals 1. So we could also say that the region is the region such that y is between 0 and 1, and x is between y and 1. And then we can integrate in either way. So we can integrate with respect to x first, or we could integrate with respect to y first, depending on how we're going to describe the region. But we want to integrate with respect to y first. And the reason is that if we tried to integrate sine of x over x with respect to x first, so if we tried to integrate in this order, the problem is that we actually don't have any method to integrate sine of x over x, or at least not integrate using elementary functions. There's probably a way to integrate if you would expand sine of x with its infinite series expansion, and then divide each of the terms by x or something, and so you could get an integral where you have an infinite series, possibly. But it's certainly going to be much more difficult than if we integrate with respect to y first. If we integrate with respect to y, then the problem actually becomes very simple. So notice that, again, this integrating with respect to x is difficult, but integrating with respect to y is going to be easy. So this integral from 0 to x of sine x over x dy ends up being easy to evaluate. So we choose to integrate with respect to y first, of course, because we want to do the easy thing. And we get the iterated integral where we have the integral from 0 to 1 of the integral from 0 to x of sine of x over x dy dx. And so we take the integral of the inside first, and we get sine of x over x times y from 0 to x. And then we plug in an x for y here, and the x from the y and the x that's already in the function sine of x over x are going to cancel with one another. So this will cancel with this essentially, and we're just left with the integral from 0 to 1 of sine of x dx. And of course we know how to perform this integral. So the antiderivative of sine of x will be minus cosine of x, and again we're evaluating from 0 to 1, so we end up with negative cosine of 1 plus 1. And so you can see that performing this double integral wasn't too difficult, but if we did it in the opposite direction, integrating with respect to x first, the problem would be very, very difficult. So the moral of the story here is to always look for the simpler order of integration and make your life a little bit easier. Okay, so let's move on to a couple more examples now. The first example here is just going to be about switching the order of integration. So we're not actually going to evaluate the integral, we'll just worry about the order in which we integrate. So the example says to sketch the region of integration for the iterated integral from 0 to 2 of the integral from x squared to 2x of 4x plus 2 dy dx, and write an equivalent integral with the order of integration reversed. So that's the goal here. Well, we are integrating with respect to y first, and we see from the limits of integration that y is going to be bounded above by the function 2x and below by the function x squared. So the first thing we do is draw a plane, which I have over to the left, and we draw the function y equals x squared and the function 2x. And then we know that x is going to be between 0 and 2, so I can draw x equals 0 with a blue dotted line, and x equals 2 with a blue dotted line, and then we look at the region that is bounded by all of the things that I've just drawn, and so that's that kind of banana looking region that I have there. And instead, we could say that x is bounded below by the function y equals 2x and above by the function y equals x squared. But of course, then we want to write the function in terms of y. So we want to give x in terms of y as opposed to y in terms of x. So to take this y equals 2x and write it as a function of y, we divide by 2. So x is equal to y over 2, and on the other side we can take the square root, so that x is equal to the square root of y, and then we can say that x is bounded between two functions of y. So it's bounded below by the function y divided by 2, and it's bounded above by the function given by the square root of y. And in this case, y is going to be between the constants 0 and 4, because you have y equals 0 down on the x-axis, and then at this intersection point up here, you have y equals 4 instead of y equals 2. So this integral that we originally had, the integral from 0 to 2 of the integral from x squared to 2x of 4x plus 2 dy dx, will be equal to the integral from 0 to 4 of the integral from y divided by 2 to the square root of y of the same function 4x plus 2 dx dy. So again, notice that the order of integration is switched here. And now we can move down to a little bit of a break here before we go to the last example, where we're just going to go through a few properties of double integrals, most of which are properties that you would probably expect. They just kind of carry over from single integrals, but there is well, no, I guess there are a few differences, but almost all the properties do just directly carry over from single integrals. So the first property is the constant multiple property, where if you have the double integral of c times f of xy, where c is just some constant, then you can pull the constant out of the double integral. So it's c times the double integral of f of xy over the region R. We also have sum and difference properties. So if you have two functions, f of xy and g of xy, and you add them together or you subtract them together, and then you take the double integral over the region R, well, that's equal to the double integral of each of those functions added together or subtracted, depending on whether you subtract or add your two functions f of xy and g of xy inside of your original double integral. We also have this domination property here. I don't know if this is given in the book, at least for Calc 1. Maybe it is, and I just don't remember. But if you have a function f of xy and it's greater than or equal to 0 on that whole region R, then the double integral of f of xy over the region has to be greater than or equal to 0. And then we also have the second property for domination, which just says that if you have two functions, f of xy and g of xy, and f of xy is always greater than or equal to g of xy on some region R, then it follows that the double integral of f of xy over R is greater than or equal to the double integral of g of xy over the region R. And this property does hold for the regular integral as well. I'm just not sure if it was mentioned in the text back in chapter 5 or whatever it was. And then lastly, we have additivity, and I know that this was mentioned in the text. So the double integral of f of xy over the region R is equal to the double integral of f of xy over the region R sub 1 plus the double integral of f of xy over the region R sub 2, where the region R is the union of our two regions R sub 1 and R sub 2, and R sub 1 and R sub 2 do not overlap. So another way to say that would be that R sub 1 and R sub 2 have empty intersection. And below I have a pictorial representation of this last property here. So we have a region R in space, which is the region bounded in blue there, and then we've kind of subdivided that region into two smaller regions, R sub 1 and R sub 2, and that last property, additivity, just tells us that taking the double integral over the entire region R is the same as taking the double integral over the region R sub 2 and then adding the double integral over the region R sub 1. Alright, finally we have one more example for the video. It's a little bit algebraically annoying, but I included it anyways just because it's an example in the book, and I figured it would show that a lot of times these double integrals are not going to be pretty to actually calculate. So let's go into this last example here. We want to find the volume of the solid that lies beneath the function z equals 16 minus x squared minus y squared, and above the region R that's bounded by the curve y equals 2 times the square root of x and the line y equals 4x minus 2, as well as the x-axis. So again, the first thing to do here is to draw whatever that region R looks like in the plane. So I've done that on the left. We have our function y equals 2 times the square root of x in red, and the line y equals 4x minus 2 in purple, and then I have the x-axis in blue, and we end up with that region bounded by those three different functions there. And if we integrate with respect to x first, we're only going to need one double integral. But if we integrate with respect to y first in this case, we need two double integrals. So let me try and explain why that's the case. So if we integrate with respect to x first, then we're looking at cross sections that are going in this direction. And the key is to notice that for these cross sections, they're going to be bounded below by the function y equals 2 times the square root of x, because every time that our line is entering our region here, it's entering along the line y equals 2 times the square root of x, and those lines or the cross sections are always going to be exiting our region along the line y equals 4x minus 2. So we can draw another arrow here. Notice how it enters at the curve y equals 2 times the square root of x, and it leaves at the line y equals 4x minus 2. Well, if we wanted to integrate with respect to y first, then we'd be looking at cross sections in the other direction. So let me pick a different color here. That should hopefully work well. Maybe, yeah, purple is probably fine. So if we wanted to use cross sections in the other direction, then notice that if we're below, or if we're between x is equal to 0 and x is equal to 0.5, then our y is going to be bounded below by the x-axis and bounded above by y equals 2 times the square root of x. So I can draw a couple of those lines here. You can see that we keep entering at the x-axis and we leave our region at y equals 2 times the square root of x. But halfway through the interval for x, so once we get over to x is equal to 0.5, now notice that if I keep drawing my lines going through the region, my lines are going to be entering at y equals 4x minus 2, and they're going to be leaving at y equals 2 times the square root of x. So basically, the entry point of these cross-section changes halfway through the integral, and for that reason, I would have to take the integral from x is equal to 0 to x is equal to 0.5 of the integral where y is bounded below by 0 and above by 2 times the square root of x. And then I would have to add the integral from x is equal to 0.5 to 1 of the integral from y equals 4x minus 2 to 2 times the square root of x, because the limits of integration are going to change in the middle of our interval for x there. So again, we're going to integrate with respect to x first, because if we integrate with respect to x, then we only need to do one double integral as opposed to two, and we're always interested in saving ourselves some work. But to do that, we need to take these functions in x and convert them to functions in y. So we take y equals 2 times the square root of x, which implies x is equal to y squared over 4. So now we have a function in y giving us x. And y equals 4x minus 2 implies that x is equal to y plus 2 over 4. So that'll be our second function in x. And again, x is bounded above by y plus 2 over 4, and it's bounded below by y squared over 4. So then, the double integral of our function f of xy over the region R is equal to the iterated integral, where we have the integral from 0 to 2, of the integral from y squared over 4 to y plus 2 over 4 of 16 minus x squared minus y squared dx dy. So we're integrating with respect to x first. And we take that inner integral, we get 16 times x minus 1/3 times x cubed minus y squared times x. And we evaluate at y plus 2 divided by 4. So we take y plus 2 divided by 4 and plug it in for x. And then we subtract what we get when we take y squared over 4 and plug it in for x. And we get this really nasty looking algebraic expression, which I don't want to read, but you can pause the video or just look at the notes if you want to make sure that things make sense here, or look in the book, that would be fine too. But yeah, you end up with this pretty nasty algebraic expression, and you can take a lot of these terms and expand them out. So you could take this y plus 2 cubed and expand that out. It looks like, well, this doesn't look like you'd have to expand too bad. But anyways, after you do some of the expansion and a lot of the tedious algebra here, and then you combine all of the like terms, you get this expression down here. And yes, doing all of that work prior to combining all of the like terms is going to be really tedious, but that's just kind of the way it is. It's hard to avoid. But you end up with this algebraic expression down here, and then you can plug in 2 and then subtract what you get when you plug in 0. When you plug in 0, you're just going to get 0. So we're really just worried about what happens when we plug in 2 to the expression. And if you use a calculator and just plug in 2, you end up with 20,803 over 1,680, which rounds to something like 12.4. So the volume of the solid that's bounded above by z equals 16 minus x squared minus y squared, and below by that region in the plane that we have drawn there, is going to be something along the lines of 12.4. So hopefully this is just a nice example for how sometimes things can be messy. Things aren't always going to look nice. And in the homework, if you get messy problems like this, I'm fine if you approximate answers as opposed to carrying fractions all the way through and things like that. I'll leave that up to your discretion. Okay, so that's the end of the material for section 15.2. Homework will be up on Blackboard shortly, and I'll be doing section 15.3 in sometime during the upcoming day.